Okay, welcome to the second half of the lecture. Now the better or the easier definition for this. So some people would also have this first and then homogenize it and use this thing. But I want to show you the complicated thing and now go to the easy thing. As I would say, is this the easy thing? This is probably in both books. So it's either Silverman-Tate, page 28, or Silverman, still page 42. And if we dehomogenize this equation, we basically get this equation. And of course, when we work with a not homogeneous equation, we always have to remember that in addition to this equation, we have this point at infinity. And again, so we want to consider elliptic curves over the rational numbers. So for us, usually, we consider those AI in Q. Later, maybe we will also allow those AI in some number field, but probably we'll stay with Q. And now, of course, what we can do, now we can turn this polynomial by change of variables and shifting some things. We can get rid of some terms just by some technical but easy computations, I think we will just go through them. So since here we usually want to work with those AI in Q, we basically do not have to care about characteristic, but I just want to remark it. Because at some point we have to divide by 2 and 3. And usually if you work with elliptic curves and prime numbers, you never consider 2 or 3. And if you do, then you're a nerd and you will have to really go into technical details, which some people like. Yeah, but sometimes it's really, it can get ugly there. So, okay. So the first simplification, let me write this. First simplification we do is we substitute y by 1 over 2 y minus a1x minus a3. So you see here we divide by 2. So if we were in characteristic 2, we couldn't do this. Don't know how detailed I want to go through with this, but I will just give you this, and if you want, you can plug it in and compute it yourself. But this is how we, let me write it. This turns into the following form. And because I said 2 is forbidden and 3 is forbidden, there will of course also be one step where we need to divide by 3. And this is if we substitute x and y by this. So I kept here the notation from the book such that you can see, if you want, in the book how those terms relate. But the thing that you have to take home is that if you're allowed to divide by 2 and 3, then you can come from the very complicated homogeneous equation to the inhomogeneous equation, then to this equation, and then to this. And basically an elliptic curve for us will be a curve of this form, plus the point at infinity. So also a bit algebraic geometry black box that I used is that I wrote smooth here, and we still have to find out what it means here, because this can still be a curve that looks like this, or a curve that looks like this, and we have to make sure that this doesn't happen. Yeah?
One question regarding the form, but of course we don't need to remember that 27 and 54 appear in this form.
Yeah, because these are rational numbers, so they can also be something over 27. This is just, I kept this so that you can look up the constants if you like. But now let me write down the definition that we I need one more step to get to the final definition, because we still have to know or find out what we have to say about this equation in order to avoid those types of curves. Okay, so how can we do this? Yeah?
Does the point at infinity then have some different, different coordinates than before? Before we had a point at infinity in k to the 3, and does it translate nicely to?
It doesn't translate at all. So we just have to, when we go from here to there, we kind of lose the point at infinity. That's what I meant by we have to remember that we still have it, but it doesn't show in our equation. Because we can only kind of get it back if we homogenize the equation again, and then plug in 0, 1, 0, and then it will be there again, or maybe with some other coordinates. But here we cannot see the point at infinity anymore. So when we still have to figure out what we have to do to avoid those, but when we have done that, I will write down the definition of an elliptic curve, which will be the points that fulfill this equation and separately the point at infinity.
Okay, but will we introduce a notion of, I don't know, distinguishing between different infinities? Because that's
So yeah, then there will not be different infinities anymore. There will only be the point and infinity that also intersects the curve, and everything else that could happen in some projective surrounding and infinity will not be of interest for us. Basically, we can forget that projective geometry even exists. So this is just because I think, so I'm not a big fan of algebraic geometry. That's why I want to use it as a black box. But I think many people like to understand some backgrounds using algebraic geometry. That's why I also wrote down this, so that you can see where this point at infinity actually comes from. But when we work with it, we don't need at all that it comes from this homogeneous stuff. And I think we will not use that anymore. We will just use the point and infinity as the formal thing that we need to make this a real group. Okay, so now the question is, what do we have to do to avoid the bad things? And so what is the problem with those 2 points? The problem of the points is that they don't have unique tangents. So the points are singular. Let me see how I want to go through that. Okay, in the books they still work with singular curves here. So let's postpone this final easiest definition to later, and we will work on a few things that will in the end lead us to what we have to say about this in order to avoid those 2. We want to introduce 2 invariants. And in the books, Silverman, still page 42. And here. Okay, maybe this is actually, this is, maybe one thing that's only in one book, because that's actual theory. So it's always, at least in algebraic geometry, but maybe in math general, we want to classify things. And we want to find something by what we can grab things. And the J invariant is such a thing. So the J invariant can be defined for every elliptic curve, and as it already, the name says, it's an invariant. In the notation that we use here, So the notation like this. Yeah. We have the J invariant and the discriminant. We will find out what the discriminant means in the next half hour, I think, and we will use this to define actually our final definition of the elliptic curve. And the J invariant is this cubed over the discriminant. What we can already see is that it would not be so nice if the discriminant was 0, because then we could not compute the J invariant. So there is already a hint that maybe the discriminant should not be 0, but we will get there. So why is the J invariant called J invariant? We will get to the first actual proposition, and I think that will be an exercise also. So it's proposition 1.4 in Silverman-Tate, page 45. But only part of it that I want to state here. We take Q here. So, okay, now the bad thing is that we haven't had a final definition of the elliptic curve, but we're still talking about properties of the elliptic curve. But in the end, everything will work out, so this is only for your gut feeling, maybe. And trust that in the end we will find a definition for the elliptic curve that will have everything that we need. So the J invariant, it just says that the J invariant is actually what we want it to be, namely it classifies isomorphism classes of elliptic curves. So two elliptic curves are isomorphic if and only if they have the same J invariant. And actually the proof is in the book, but I still want to put it as an exercise on the sheet, so you actually have to write it down. You can think without the book, or you can just copy it from the book, but the way to get there is to prove that over Q bar, so we don't have to worry about characteristics to make it a bit easier, that over Q bar we can always no matter in what form the elliptic curve is, either in that form or in that form, if it has the same J invariant, it's the same curve. So we can go through change of variables, change of coordinates from the other one curve to the other, and also the other way around. So if two curves are isomorphic, if we can have some changes that we can make, then they have also the same J invariant. This is, I think it's only a few lines. but it's good to think about it and write it down. And also very nice, but you also have to write it down once to have it in your head. Basically says it's a one-to-one correspondence. Of course, every elliptic curve has a J invariant because we just defined how we can compute it, but every J invariant has an elliptic curve. So this is just, I think everyone probably knows what that means. We take Q and take the smallest number field that contains Q and J0, and J0 is just some algebraic number. Yeah, of course, we could also take any other field here with characteristic different from 2 and 3, or we could also take smaller fields here. But the core of this statement is that you can just write down the elliptic curve when you get the J invariant. And this is also in the book, but you have to write it down once. Ah, no, this is what I want to write it. I want to prove it here. At least I wrote down that that's my plan. So, can you see this here? Not so well, right? Maybe I will clear the other board because it's not large enough. Na, muss ja noch drauf schreiben können. Okay, we have to make a small case distinction. For the case where the J invariant is not 0 and not 1728, whoops, we can just write down the curve. And yeah, now it's a good thing that I used those the notation from the book, because here we did not, here we still have to do the step where we get rid of this, or we just look up the equation that was here, how we can compute from this equation the J invariant and the discriminant, which is of course here in the book, with the list of all the variables. I don't know how to write this down. Let me say, so there are two tables in this book where they describe what happens with the coefficients when you do the translations or the changes of variables. And there you can look up how to compute the J invariant and the discriminant depending on which form of the polynomial you have. Because, of course, if you actually do things with elliptic curves, you don't want to always by hand transform the equation so that it's in a nice form. You can just look up how it correlates and get that this elliptic curve just has J invariant J0. Of course, we excluded 0 and 1728, so we also have to give examples where we have elliptic curves with those J invariant. And here we have this. And for 1728, we have this. Okay. Okay. So we still have to find out what's with this discriminant being 0 or not, and what does it have to do with our singular versions of the curve. Yeah. Silverman-Tate. Ah, nee, Silverman, ja, stimmt. Ja, ja, thank you. So, here we are again in Silverman-Tate, page 47. Yeah, page 47. Okay. So, yeah, maybe we know from linear algebra 2 or algebra 1, I don't know how the curriculum here is, that the discriminant of a polynomial, so this is, we call it the discriminant of the elliptic curve, but it's also the discriminant of the polynomial above, that the discriminant of a polynomial tells us if there are multiple roots, and because if you look here, this is exactly our problem here. We have here a root that's has multiplicity 2, and here we have a root that has multiplicity 3, and the discriminant, which can also be written, well, let me think, how do I, tells us things about this. So let's consider an elliptic curve, y squared equal to something on the right side, and yeah, our coefficients are now in Q, and if we just factorize this, we will have algebraic numbers here. Well, actually, we don't care where the alpha I live, but over C or over Q bar, we can factorize all polynomials. And now we look at the two different cases of our singular curves, and we basically see that the problem is when 2 or 3 of the alpha i's are the same. Or this is what we want to avoid. And the definition of the discriminant of a polynomial squared is this, and we can maybe we can make it as an exercise or maybe it's not so important. We can show that for the form that we have here, this discriminant is the same as this discriminant. And as we can see by looking at it, if 2 of the alpha I are the same, or even also if 3 of the alpha I are the same, this will be 0. And it's an if and only if. And if we now look at what cases we want to avoid, then we see this is actually everything that can happen. Another way of writing that down is also, I don't know if this would be treated in something like algebra 1. If we look at a polynomial and its derivative, And if they have a common factor, then there's a multiple root, and then the discriminant is 0. So this is the same, and this is also bad. So we could either just look at this polynomial, or this polynomial, and take the derivative and see if they have common factor, or we can compute this discriminant and see if it's 0, or compute this discriminant and see if it's 0. But this is all equivalent, and this is everything that we need to exclude those cases. And now we're ready to come to a final definition of elliptic curves, and I think it's wonderfully planned in time. Let me think how I can start. An elliptic curve over Q. Oh, ich weiß nie, wie rum es ist. Äh, 16. Ja. Okay, so what we have now is an equation like this that we transformed from the homogeneous equation, where we got rid of some terms and some other terms, in case of characteristic not equal to 2 or 3. And then with the condition that the discriminant is not 0. And with always keeping in mind that we still have this point at infinity that we have to carry along. So there are now different kinds of how we use this wording. So sometimes we say an elliptic curve is an equation like this, but kind of what we want to work with are the points on the curve. So this is basically also what we consider an elliptic curve. So theoretically, one thing is an equation and the other thing is a set or a group, as we have seen. But sometimes we just mix those words. So sometimes we just say this is an elliptic curve and either mean the equation or we mean the actual points. But usually we mean algebraic points. So they have 2 coordinates, algebraic numbers, because this is an equation that fulfill this equation and are in Q bar, and together with a point at infinity that in this setting doesn't have coordinates, only in the homogeneous setting, and this is our elliptic curve. And to this we can also attach the J invariant, which will then be oh, I mixed this. This is the J invariant. Sorry. So this should not be 0, so the lower part here of the J invariant. To this we can attach a J invariant. We can also, so we only have here the definition over Q, but we can always keep in mind that this is also a definition that we can use whenever we are in characteristic not 2 and not 3, because this is the route that we went from the homogeneous polynomial that works for any characteristic, and then we divided by something with 2 and 3 and got there. But since we are not interested in 2 and 3, this is not a problem. Okay, I think that's a good point to stop. Yeah, but this is basically, yeah. Also, the 16 is not that important because usually we're interested in primes that divide the discriminant that are not 2 and 3. So something like minus 16 is not interesting. More questions? Okay, then thank you for your attention and see you next week.
One thing, because we don't have an exercise session on Monday, I have a locker, I don't know.
Ah, yeah.
And in the exercise sheets at the usual place, meaning right outside and diagonally on the other side. There are some things where names are written on, and I'm on the lower right, I think. There is written on algebraic number theory, Julian Reichardt. So please send it in there, and please put your name on the sheets, because I'm sharing this with another person. And this, well, it's analytic number theory, other person, so it should be easy to distinguish them, but still, please put on your name, put them together with some, yeah, and you can hand it in pairs. Okay.
Yeah, sorry, forgot that. Thank you.